We were disrupted by a fire alarm, but thankfully nothing was on fire. All right, back to this. We've got these two patty cakers. We have some values in terms of their pre-blast-off scenario. We've said that momentum is being conserved. We set the momentum before equal to the momentum after, and we're in the process of isolating for the final velocity for patty cake friend B. And I think we're just about there. We're ready to sub in our values. Now, as we sub in our values, I am actually strategically leaving myself space over here because I want to be able to do something else afterwards. So if you're laying yourself out differently, that's fine. I'm just telling you that that's what I'm doing, okay? We got our VB primed all by itself. And we could write out the answer and say that we've got MA, VA, M plus MB, VB minus MA, VA primed all over MB. I want to point out that we can't just cancel out the masses because they're not the same mass, right? Mass A and mass B, so I can't eliminate that mass in the denominator. What I can do at this stage, so I'm going to leave this here as a nice generalized equation for this kind of a one-dimensional explosion. But we could also recognize that VA equals VB, in this special case, equals 0 meters per second. So in this case, what can I get rid of? First two terms in the numerator, right? So boom, those guys are gone because VA and VB are equal to 0, but only because this is a system that starts from rest. If they'd been gliding along together before they blasted off, it would be different, right? So we got negative MA, VA primed over MB, and subbing in values, we end up getting negative of 100 kilograms times VA primed, which was 5 meters per second. This negative sign here is because of algebra, not because of reference frame, just to be clear. And then divided by MB, 50 kilograms. Now, these two friends happen to be in a 1-to-2 ratio in terms of their masses. So there's don't think that there's patterns that don't exist here. We'll see something. But 5 times 100, 500. 500 divided by 50 is 10. But negative 10.0 meters per second, or 10.0 meters per second to the left. Which is, I think, exactly what we were kind of predicting, was that this person is going to, VB, is going to blast off at a speed of 10 meters per second, or sorry, at a higher speed than VA primed, which was 5.00 meters per second to the right. Now, it happens to be double, but remember, the reason that there's that 1-to-2 ratio is because their masses were 1-to-2. Okay, so that's just kind of a pattern that's popping up. That might not be as apparent if the ratios of masses aren't quite the same. Something else that we might talk about is if we weren't discussing people playing patty cake, because that's all fun and games, but if I were to have a particle emitter, you imagine that there's this particle emitter, let's just call it the particle emitter 2000, because that sounds like a good branding. But let's just say that it fires out particles, right? And that's its whole thing. It shoots particles out, and these particles might be, subatomic particles getting fired out, and they're made up of multiple other subparticles. If these things were to spontaneously decay, can you imagine that sometimes they would fire off so that there'd be a boop, 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 and then when it decays, some of them go off this way, and some of them go off this way. Now, in this situation, remember, the momentum of the original particle is going that way. The momentum of this particle here is going off this way. The momentum of this particle is going off this way. But can you see that the sum of those two momentums would add up tip to tail? Like this. So that their resultant momentum would be the same as the original particle, right? So when we talk about these kinds of things, conservation of momentum, we're not really just talking about roller skating patty cake buddies. We're trying to build a foundation of thought for other things, right? Like, so sometimes scenarios like this seem silly and inapplicable, and really, like, what physicist is ever really analyzing patty cakers? Probably we're building a foundation for subatomic particle decay or something like that, okay? So I'm just putting that out there that, yeah, I'm trying to be a little bit silly about this, but also want to make it accessible, and yes, I'm definitely still going somewhere with it, okay? All right, so there's this other thing, and in the past we've talked about cannons, and sometimes when we talk about cannons, we'll talk about cannons in terms of Newton's third law. You know, like there's a cannon that pushes on a ball, but actually the ball also pushes back on the cannon. That's actually not necessarily the best way to talk about it. Think about this. If I had a particle emitter, like the particle emitter 2000, and it fired out a particle, that particle is going to have its own momentum, right? And that particle is going to have a small mass and a big velocity. What's going to happen if there's going to be conservation of momentum? What's going to be true about the momentum of the particle emitter? Isn't it going to have a momentum as well? Because before it emitted a particle, the momentum of the emitter was zero, right? Kind of like our patty cakers. So then if this guy gets a, let's even call it P primed and V primed for, let's just call it a, I don't want to call it a P for particle because that'll be too many P's. We'll have PP all over the place. But if this one also has a P primed, let's call it P primed A, VA primed. This guy here would have a momentum going back the other way. This momentum, can you see this momentum and this momentum would be the same magnitude but opposite direction because the sum of them would have to be zero because it was zero momentum before we started, with our, just like with our patty cakers. So we would have a PB primed going back this way. And of course with this one, the emitter has a big mass, and the emitter would recoil with a ridiculously small V prime B if you like. In fact, so small that if you fire subatomic particles out of a particle emitter, you're not even going to notice the recoil momentum at all, right? Because there's going to be such a small velocity, it'll be, well, really unmeasurable, actually. But there would be some, because conservation of momentum is a thing. And if you take this and you kind of scale it up and say, well, it's not just a particle emitter. Let's try and use this as a propulsion system. This is actually what a rocket is all about. Now, with a cannon, you actually do get recoil because the mass imbalance, if you like, isn't like so lopsided as a particle emitter. But when it comes to a rocket ship, it turns out that it is very lopsided, and this particle emitter that we usually call a rocket ship, and that's literally what a rocket ship is. It's a particle emitter where we direct the particle emission nozzle that way, and maybe we would put a cone on it, and maybe we put fins on it, and now it's called a rocket ship, and it emits particles out the back end, and every time one of those particles gets emitted, it's the same idea, that there's momentum out the back end, P primed for those particles, and momentum primed for the rocket. And people say, well, how come the rocket actually gets propelled forward? Because you're not just emitting one particle or a few particles. You're emitting like Avogadro's numbers worth of particles. Tons, right? Like an absolute ton of particles. That's what rockets do. They emit particles with lots of momentum per particle, and that momentum is cumulative because conservation of momentum is a thing, and that's what propels the rocket forward. It's not Newton's third law. There's not an action-reaction. It's better to think of it as a conservation of momentum, particle emitter thing, okay? And if you wanted to like scale this to a human level or whatever, you can honestly like sit there on, you know, like those office chairs that have like, I don't know, you guys picture this, like those office chairs that have the wheels, and they usually will have like, did I get that right? Yeah, 5 wheels, because that like promotes stability or something like that. And if you have a person sitting in this office chair, and you give them like a stack of, oh, this is starting to become a bad cartoon. But if you give them a stack of textbooks, and you stack that stack of textbooks on the person's lap, and you say, okay, you got to propel yourself. The easiest way to propel yourself, if you have a stack of, let's just say, biology textbooks, because you'd never do this with physics textbooks, right? And you just start tossing biology textbooks off of your lap, what's going to happen to the person? Each one of those biology textbooks has momentum. Yeah? Yeah. The person on the the system, like the person and rolly chair system is going to go that way. You can imagine that? You can use textbooks as a propulsion system. If you want it to be even better about it, you can probably find YouTube videos. You could replace your textbooks with a fire extinguisher. For real, people do this, right? Don't do that in my classroom, but you could do this. And if you sat in this rolly chair, you could fire a fire extinguisher in the same direction that we just threw a textbook, and it would actually start to get more like a rocket ship, right? Because you're going to be shooting like an Avogadro's number level of particles, fire extinguisher particles, whatever that is. I have to look that up in a chemistry textbook. Good thing we only threw away biology. But I mean, like, this is something that, I'm just joking. I'm just joking. Everything has value. And I really love biology. Just being silly, and I expect somebody's going to go tattle on me or something. But anyway, anything that you can throw one way is going to propel you the other way, and it has to do with conservation of momentum. And I think that's kind of a nice thing to pull out of patty cake, is that you can, from patty cake, actually learn something about rocket science and particle decay, and that's cool.